So in this video, what we're going to do is we're going to go through some systematic procedures for writing and balancing chemical equations. So as we mentioned previously, we write an equation with the reactants depicted on the left separated from the products by an arrow which are written on the right of the page. If I've got multiple reactants or products, I'm going to write them separated by a plus sign. So this chemical reaction at the bottom here would be read as hydrochloric acid reacts with sodium hydroxide to produce sodium chloride and water. The reactants that are written on the left are also sometimes referred to as the reagents with a G, or also the starting materials. And you just kind of have to get used to people using these synonyms for these things. It's okay. You'll get used to it. We will often indicate the state of each substance after its formula by putting the symbol for the state in parentheses. And often, if the substance is dissolved in water to form what we call an aqueous solution, we'll indicate that with the letters AQ in parentheses after its formula. So it's good to know these things, because if we have something like H2O, if we write that it's solid, we understand that the temperature is less than or equal to 0 degrees Celsius. And if we have something like H2O gas, then we know that that is steam and that the temperature is greater or equal to 100 degrees Celsius. Now, if we have something, and we'll see this later on, like Fe, that's iron and liquid, then we know we have a very high temperature because, well, molten iron doesn't become molten until a very high temperature. So those state symbols can be quite important in letting the person who's reading the chemical equation know what's going on. As I mentioned in the previous video, we balance the atoms in a chemical equation by placing coefficients in front of the formula, and these coefficients act as multipliers. And we said that we always try to make the set of coefficients that we use to balance the chemical equation the smallest set of whole numbers possible. So if we can, after balancing, we will divide through by a common multiple in order to get the smallest whole number set. Now similarly, if I had something like 1/2 a methane reacts with 1 O2 to form 1/2 a CO2 and 1 H2O. Now, while that is balanced, it is balanced. While that is balanced, this is not the smallest whole number set of coefficients. So I'd actually multiply everything by 2 in there to get this up to a whole number set of coefficients. And we're going to see that later on as well, that sometimes when we balance, we actually have a fraction in there and we need to multiply to remove that to get the smallest whole number set of coefficients. So let's have a look at a moderately complex balancing problem. So it says balance the following equation, and here are our reactants, here are our products. Okay, so what I'm going to do is generally begin with the most complex compound and balance for all of the atoms that are present in that. So the one that has the greatest variety of atom types. And I'm going to start in this case with this guy. So what I see is that I've got 3 iron atoms in here and I've got 4 oxygen atoms. But when I go over to the right hand side, I see I've only got 1 iron atom and 1 oxygen atom. So what I need to do is to get this 1 up to 4, and then to get the iron up to 3. So let's do that. So what I'm going to do is I'm going to put a 3 there and a 4 there. So now I'm at this situation where I've balanced for the iron and I've balanced for the oxygen. So I'm done with that guy and I move on to the next thing. So what have we got going on now? Well, on the left, I've got 2 hydrogen atoms, and on the right, 4 times 2 I've got 8 hydrogen atoms. So what I'm going to need to do is multiply that guy by 4. So when I do that, it looks like this, right? Fe3O4 plus 4H2 gives 3 ions and 4 H2Os. So if I check everything, I've got 3 ions on the left, 3 ions on the right, 4 oxygens on the left, 4 oxygens on the right, 8, 4 times 2, 8 hydrogens on the left, 4 times 2, 8 hydrogens on the right. So everything is balanced. So the only difference between the unbalanced equation and the balanced equation is that in the balanced equation, I added a few coefficients. Sometimes you only have to add one coefficient. Sometimes you have to add a coefficient for every reactant and product. It depends. Occasionally, you'll write a chemical equation out and the stoichiometry is all 1 to 1 to 1 to 1, and you don't have to add any coefficients. But the only way we balance a chemical equation is by leaving the formulas alone and adjusting the coefficients. So let's have a look at a more complicated one. This one's complicated because it has what we call interfering coefficients. So let's see how this is going to play out. So we've got C4H10 reacting with oxygen to make carbon dioxide and water. So this looks pretty complicated. So I'm going to begin with that guy and I'm going to start balancing for carbon and hydrogen atoms. So on the left I've got 4 carbon atoms and I've got 10 hydrogen atoms, and on the right I've got 1 carbon atom, and 2 hydrogen atoms. So I'm going to want to multiply that guy by 5 and I'm going to want to multiply that guy by 4. So it looks a little messed up at the bottom here. Let's just fix that. Maybe what we can do is just move these guys above it. There we go. Alright, there we are. Much better. So now we have 4 carbons on the left, 10 hydrogens on the left, 4 carbons on the right, and then 5 times 2, 10 hydrogens on the right. So that looks good. So we're done with that guy and we move on to our oxygens. So when I look at the oxygens, what I see is I've got 2 oxygen atoms on the left, but then I've got 4 times 2, that's 8, plus another 5, that's 13 oxygen atoms on the right. So how am I going to get 2 up to 13? I'm going to have to multiply by 13 on 2, which is the same as 6.5. So I put a coefficient of 6.5 in front of the oxygens, and now what have I got? 6.5 times 2, I've got 13 oxygens on the left, and then 4 times 2, that's 8, plus 5, I've still got 13 oxygens on the right. Now, of course, what we see is that we've got a fractional coefficient. So I have to multiply to get rid of it, right? So I'm going to multiply everything by 2 to get rid of my fractional coefficient. So 2 there, 13, 8, and 10. So there we go, and now when we check everything, it balances. So I've got 2 times 4, 8 carbon atoms on the left, 8 carbon atoms on the right. 2 times 10, 20 hydrogens on the left, 10 times 2, 20 hydrogens on the right. 13 times 2, 26 oxygens on the left. 8 times 2, that's 16, plus another 10, that's 26 oxygens on the right. So that's it. That's how we get rid of a fractional coefficient. So it's often seen that we'll end up with a fractional coefficient when we first kind of try and balance when we have one of these diatomic elements present. So that's what happened here, right? We had O2, so we ended up with an odd number of oxygen atoms on our right hand side from our initial attempt of balancing, and that led to us needing a fractional coefficient on the left, and so we had to multiply through at the end to remove that fractional coefficient. Alright, So let's have a look at some of these problems from Alex that are going to be about balancing equations. So it says, what is the total number of oxygen atoms on the right-hand side of this chemical equation? So oxygen appears in two spots. There's 3 oxygen atoms here in this calcium carbonate, and then there's another one there, so that gives me 4 oxygen atoms. So being able to correctly count up the number of atoms of a given type in a formula is, the first step in being able to balance. Okay, so this one says balance the chemical equation below using the smallest possible whole number stoichiometric coefficients. So let's see what we've got. And this is non-interfering coefficients, so it's going to be an easier one. So carbon solid plus H2 gas gives C2H6, that's called ethylene gas. We can see immediately, let's just begin with the carbons. We've got 1 on the left and we've got 2 on the right. So I'm going to have to multiply that guy by 2. And then I move on to the hydrogens. I've got 2 on the left, but I've got 6 on the right. So I'm going to have to multiply that guy by 3. And now it all balances. 2 carbons on the left, 2 carbons on the right, 3 times 2, 6 hydrogens on the left, 6 hydrogens on the right. It was pretty easy. So 2, 3, 1. Note that you don't put the 1 in. That's considered to be incorrect. Okay. Now we're going to balance with what we call interfering coefficients. So we're probably going to end up just seeing as we've got a diatomic there with a fractional coefficient when we first balance, but we want the smallest possible whole number set of coefficients. So let's see how this is going to work out. So we got CH3 plus O2 gives me CO2 plus H2O. So let's begin with balancing for carbon. So 2 carbons on the left, 1 carbon on the right. So let's multiply that by 2. Okay, now we're going on to hydrogens. 3 plus 3, that gives me 6 on the left. And then I've only got 2 on the right, so let's multiply that by 3, and then that'll balance. And now oxygens, which is where I'm anticipating the awkwardness. So I've got 2 oxygens on the left, and then 2 times 2, that's 4, plus another 3 oxygens on the right, so that is 7. So I'm going to multiply this by 7 on 2. Okay, so that is actually balanced now. Yeah, it's all balanced. So the only difficulty is that I don't have this whole number set of coefficients. So I'm going to have to multiply everything by 2 to get it up to a whole number set. So let's go ahead and do that now. So that's going to be 2. That's going to be 7. That's going to be 4. And right here will be 6. And now everything balances. So if I look at carbons, 1, 2 times 2, 4 on the left, 4 carbons on the right. Hydrogens, 6 times 2, 12 on the left, 6 times 2, 12 on the right. And then finally oxygens, 7 times 2, that's 14 on the left, and then 4 times 2, that's 8, plus another 6, that's 14 on the right. And if I look here, I can't get a smaller set of coefficients without going to fractional coefficients. So that is the smallest set of whole number coefficients. Now, this equation was written with the state symbols included. So when I write it out, I should also include the state symbols. But, I didn't want to do that until I'd finished balancing. Now, because the water here is present as a gas, I know that this is going to get hot, this reaction, right? There you go. So it has to be above the boiling point of water. Okay, so that's some systematic procedures for writing and balancing chemical equations. I hope you found the video helpful, and I just want to point out that I put a little extra credit assignment on balancing chemical equations. It's a little video game where you just have to see how quickly you can balance a series of chemical equations that are like in increasing level of complexity. So have a go at that and earn yourself a few extra credit points.